Hello. In this screencast, I just wanted to help you figure out some equations we commonly use in physics to describe constant acceleration motion. Okay, so you'll recall with the constant velocity unit that we did, you essentially had one equation. Um, so I'm going to contrast this one equation with our equations for constant acceleration. Okay. So let me group this together and see if I can move this down a little bit. On the left side, I'll put constant velocity motion. That's where you're going in one direction and your speed isn't changing. All right. On the right side, I'll do constant acceleration. And we'll do the graphs. And down below, we'll do the equations. Okay? And I'll try to do a nice job here. Whoops, haha, fix that. Try that one again. So, hold on. Just give me a second here. Oh, that was good. That was horizontal before I messed it up. Last try. This time it'll work. Okay. There we go. All right. And, okay, description of the motion, we'll call this constant velocity. And on the right side, we'll call this constant acceleration. And this is when the velocity is changing. The same amount each moment in time. That passes. Okay? Constant velocity is the opposite of that. When the velocity does not change. So let's contrast our velocity. Let's say it's measured in meters per second. Okay? A velocity versus time graph. When an object is moving with constant velocity versus a velocity time graph when an object is changing its velocity the same amount each moment. Okay? Now, you may have a graph that looks like this. You may have a graph that looks like this. You may have a graph that looks like this. Which one of these is constant velocity? The red, blue, or green? Pause the video and think about it. You want to see the answer, okay, you can watch the video again. So hopefully you paused it and you thought about it and picked one. Red's definitely not constant velocity. Green's not constant velocity, but blue is actually constant velocity. So I'm going to delete the other ones and redraw blue. Okay? I could do a little bit better of a job. The reason it's a constant velocity is because this graph has zero slope, meaning there's no change in whatever's on the vertical axis. So zero slope actually means there's no change in whatever that variable is. Now let's try this one. You could have a line looking like this, maybe a line looking like this, or maybe a line looking like this. So I wonder what the difference would be. Well, pause the video and think about which one of these is going to be constant acceleration. Okay? I'll wait a moment while you think about it. Okay, hopefully you paused the video and actually thought about it. Truth is, all of these are constant acceleration. Every one of them. Any line on a velocity graph is going to be constant acceleration. Now, if I want to get all technical, the blue line, the velocity is not really changing. The velocity is staying at the same value. But I could also argue that that's an acceleration of 0. So it does fit the definition of constant acceleration because the entire time the acceleration is staying at 0. So all of these really are constant acceleration. The red line is a positive acceleration, meaning in this case, the red line means in this case, because these values of velocity are above the t-axis, the numbers on this vertical axis would be getting larger, meaning that your speed is increasing. And you're moving in the positive direction because all these numbers are above the t-axis. Now, we could do the same graph or the same set of graphs down below. Let me just group these together. Okay, and I'll clone them. Okay, and I'll put them down here. Drawing these same exact graphs down here still means the same thing, except, let me ungroup that real quick. Well, all of these are still constant acceleration. The blue line still means that your acceleration is 0. The green line, when it's below the t-axis, is going to mean that my numbers are getting bigger, therefore I'm speeding up. But when the green line's above the time axis, the horizontal axis, I'm actually slowing down. The red line, when it's below the t-axis, I'm actually slowing down. But when the red line's above the t-axis, I'm speeding up. So looking at what these numbers would be on the vertical axis and imagining the pattern and how they're changing will probably help you figure this out. Anyway, so what I want to do now is I want to take this position time graph and hold on a second here. Let me try to fix this. There we go. Let me get rid of that. That's confusing. Let's delete that. Okay, and I want to write an equation. All right. Constant velocity. Our equation is just v equals some number. Okay. So I'm going to put a number here and make it 4 meters per second. So there's my equation. Now, more interesting than that, if I take the area of this graph, so let's make this, I don't know, let's call that 4 seconds, okay? Now I can find the displacement, okay? That's the change in position. So change in position, called displacement, is going to be velocity times time. So in this case, it's 4 meters per second, 4 seconds. And that's going to give me 16 meters. Okay? Now that's 16 meters in the positive direction is how far I moved from where I started in the positive direction. So it looks like my object moved 16 meters in the positive direction from where it started. Now, I don't know where it started. It could have been any position, okay? And in general, then, this equation becomes delta x equals velocity. See, this is our velocity times time. So velocity times time. Change in position is my final position minus my initial position. Okay? And that's equal to, I'm going to use symbols now. V is a common symbol for velocity. T is a common symbol for time. And if I solve this equation for final position, I get velocity times time. See, I add x naught to both sides of the equation, and I get vt plus x naught. Okay? This is a general equation for any object moving with constant velocity motion. That's an assumption you make when you're using this equation. If you do not have constant velocity motion, you cannot use this equation. Okay? And I should remind you that velocity is change in position divided by change in time, otherwise called the slope of a position-time graph. Okay? So that was a review of constant velocity motion. And those are our equations for constant velocity. This one being extremely useful in a lot of different situations. Now, if I want a general equation for all of these possibilities of constant acceleration, you notice all of these are in line. So that means I would have velocity equals some slope times t, which is time, plus whatever the vertical intercept is. Okay? That would be my equation for all of these lines. Now, this slope could be positive or negative. The intercept could be positive or negative, and that determines which of these lines we're dealing with. Okay? This slope could even be 0, which it is for the two blue lines. In general, the slope of a velocity graph is acceleration, right? Change in position divided by change in time is velocity. Change in velocity divided by change in time, by definition, is acceleration. So the slope of this velocity graph, all of these 4 different lines, 6 different lines, these slopes are all your acceleration. So in general, we have velocity equals acceleration times time plus whatever our vertical intercept is. Well, the vertical intercept is a velocity at 0 seconds. So I'm just going to write velocity at 0 seconds. Okay? So in symbol form, this is a very useful equation. When we have constant acceleration motion, it's v equals a times t plus velocity at 0 seconds. And remember, we can only use this for moments in time when the acceleration does not change. In other words, the acceleration is constant. Now that's one of our equations that we use for constant acceleration. There is another that's highly useful. Along with these graphs, we can also draw an acceleration time graph. Okay? So let me shift this up a little bit. Move this over here. Okay? I'll move these words. Move these words a little bit. Whoops. That might work. That's pretty good. That'll work. Move this up a little bit more. That was good. Whoops. Okay. There we go. Now I want an acceleration time graph real quick. All right. Now, if you have constant acceleration motion, right, that means you have acceleration on this axis measured in meters per second per second. So each second, your velocity is changing by a certain amount of meters per second, right? And time is measured in seconds. So let's see here. For both of the red lines, we have a positive acceleration because the slope on our velocity graph is positive. For both of the blue lines, we have 0 acceleration, right? And for the green line, we have negative acceleration. Okay? Now, the area under our acceleration time graph, let's take this one. This area. Or if you have the green line, it's this area. Now, you'll recall that the area under a velocity time graph is change in position, but the area under an acceleration time graph is change in velocity. So if I take, I'm just going to make up a number. Let's say my acceleration is 4 and for 10 seconds. So let's say I speed up for 10 seconds in the positive direction. So I'm moving in the positive direction. This would be the top graph right here in red. So I speed up while moving in the positive direction because all those velocities are positive. And then this rectangle shows me my change in velocity, right? This trapezoid shows me my change in position, change in x, okay? This rectangle is my change in velocity, which in this case would be 4 meters per second squared times 10 seconds. And my change in velocity, therefore, would be 40 meters per second. And it's a positive change in velocity. So this means my final velocity, whoops, I don't know what I just did, whoops. This means my final velocity minus my initial velocity at 0 seconds is equal to 40 meters per second positive. Okay? This does not tell me how fast I'm going at this moment. This tells me my change in velocity from 0 seconds to the final moment in time. But in general, we can always say that change in velocity is the area under an acceleration time graph, which is going to be a rectangle for constant velocity motion. So change in v is going to be the acceleration times the time, right? So I can use this in conjunction with this equation here. So I can substitute one equation into the other, okay? So again, change in v is equal to AT, right? So that means that v final minus v initial is equal to AT, right? And if I take the area underneath this graph, notice it's a trapezoid. So the area of a trapezoid, let me redraw this down below. So we got a velocity time graph that looks like this, and we got an acceleration time graph, for example, that looks like this. Okay. Notice this shape here is a trapezoid. This value at the end is my velocity at the end, v final. And this value here is my velocity in the beginning, just by reading the graph. And taking my acceleration graph, that area is equal to my change in v, which is at. Right? Now, this area right here is going to be the average of my initial and my final velocity times the time. Okay, that's one way of writing it. Okay, I can take the average of these velocities. That effectively, an area of a trapezoid is really the area of a rectangle that's has a height halfway between v naught and v final. Okay, so if I take the average of v naught and v final times time, so I go 1/2 v final plus v naught, and I multiply by time, that's one way I can find my displacement. Okay, there are other ways. For example, I'll redraw the same graph, v times t, okay? And I can turn this into a triangle, and I can turn this into a rectangle, okay? And I can make my initial velocity, I can label that, that's my velocity at 0 seconds, and then trace this over. This is my final velocity, vf. And let's add those, the triangle and the rectangle, okay? Oh, whoops. I didn't want to do that. Great. Okay, so let's do this. The rectangle is going to be v naught t plus, now this height here is going to be v final minus v initial. And I got to do 1/2 because it's a triangle times t. So this here is the area of that triangle. This here is the area of that rectangle, right? And together, these are going to equal our displacement, right? Our change in position. Okay? So let me rewrite this, make it look pretty. Delta x equals v naught t plus 1/2 v final minus v naught times t. Okay? And these are all vectors, meaning that these are numbers that have a direction. Okay? Let's see, what could I do now? Well, I have this equation here. From the area under my acceleration graph, I can take this equation and put it there. And this will be the last step, dude. So v final minus v naught is going to be equal to at. So this whole thing now is going to be at. I can substitute at in place of that. And that's nice, because then this is AT times T. 1/2 here plus delta X equals V naught T. All right. Now, gosh, looks like 1/2 AT squared. So we have a way to find displacement for objects that are moving with constant acceleration. Quite a powerful equation, quite useful. And this A can't be a changing number, it has to be constant. Acceleration. For us to use this equation, we must assume the velocity is changing the same amount each second. And that's because we use this graph to actually derive the equation. And this graph is assuming constant acceleration. Anyway, these are your fundamental equations. You got this one here. And you have, try that again. And you have your equation for velocity. Where is it? There it is. So you have a nice way where you can find the velocity of an object that's moving with constant acceleration. So you can find the velocity at any moment in time. And you have a nice way of finding the change in position from beginning to end. Now, if you want your final position, if you happen to know your starting position at 0 seconds, this equation's easy to modify because delta X is final position minus initial position. So if you solve this equation for delta X, you'll get X final equals, now because it's minus X naught, the X naught goes to the other side. You get X naught plus initial velocity times time plus 1/2 AT squared. Now, essentially, these equations are the same, except the second one is like used when you know your exact positions at 0 seconds in it and in the end at time t. On the other hand, this top equation is nice if you want to work with displacement instead of position. Okay? Anyway, thanks for watching. I hope that was enlightening, and I hope you have a good night.